Hi everyone, this talk is about stringly typed to strongly typed with TypeScript. Just want to start off by saying a big thanks to our sponsors. So I'll start off with who I am. Currently working at VGW as a senior software engineer, and I pretty much all the time working on TypeScript and Node, so most of my stuff is on the back end, but obviously I do some front end stuff as well, also in TypeScript. I've been using TypeScript and Node since the very early days. I used to think that if you really pushed a language to its absolute limit, you'd be lucky enough to discover a bug that wasn't your bug, it was actually a bug in the compiler. And over the years of using TypeScript, because it's been, it started small and it's become more and more popular, but I've discovered a lot of those bugs. So either I've really been pushing it to the limit or it's a very buggy project. I think the truth is a bit of both. Although I'd like to say that now I rarely open new issues on TypeScript, so it's a really solid platform now. Same with Node. I also like to contribute to open source projects and maintain a few of my own, and also like to mentor at CoderDojo in Perth. So I thought it was relevant to actually talk a little bit about who you are as an audience as well, because I figured who would be interested in a talk about TypeScript. And it's a well-known language, but not everyone's using it yet. And I figured that there's probably a few different groups in the audience. So I guess most people here are developers. Some of you might be more familiar with dynamically typed languages. If you're working on the front end, you're probably using JavaScript. There'd also be a bunch of people who are familiar with PHP and Python in particular, if you're working in sciences or anywhere for that matter. Other popular languages are what they call the statically typed languages, and they're things like C#, Java, Haskell, C++, things that require you to explicitly add types to your code and satisfy the compiler that your code is correct. And there might also be some people here already using TypeScript. So I'm aware that I'm probably speaking to several different people and who have different questions. So if you're already using dynamic languages, you're probably asking yourself, like, why do I want to add steps? Why do I want to add a build step and all these checks? It's just going to slow me down. So, what's the deal? If you're mainly used to using statically typed languages already, you're probably wondering, well, why would I do the next project in in TypeScript? What's in it for me? What am I going to gain? And if you're already using TypeScript, maybe you're here because you want to feel awesome and maybe pick up something new. So I'm going to try and cover different questions for different people. Right, so what is this talk actually about? Stringly typed code, what does it mean? I think as tech people, we should probably start with a definition. So the definition for this talk, and just as background, the term itself, stringly typed code, the name of what we're talking about, came from, as far as I can figure out, from a 2012 article on coding horror. There was an article titled New Programming Jargon, and it's worth having a look at this because it's got some other funny ones on there as well. But it had an entry for stringly typed code with this meme cat on it, which sort of sums it up. Can I use a string to store a date value? So there was a whole big text blurb. I won't bore you with that, but the summary of what it said was that it's basically about overusing strings for too many things and listing some issues that come about from doing that. I'm not going to go with that exact definition for this talk because things have moved on. We've got new possibilities with our languages and our tools and our platforms. So it's not just really overuse of strings, but it is a pattern in the code. And this is the definition I'm going to go with for my talk. So it's a coding pattern where you can make trivial errors in the code which pass static checks, but they fail at runtime. So I'm going to go through each of those highlighted bits of that definition to just sort of explain more what I mean about each of those now. So what do I mean by coding pattern? First of all, it's not a bug. Stringly typed code is not a bug. It's usually found in systems that are actually working. So we're not talking about a bug here, we're talking about a coding pattern. The issue is usually more about what happens when someone needs to change the code. Has anyone ever worked on a system that never needed to change? It's probably pretty rare. Every system I've ever worked on, there's always new requirements, even if they're not new requirements for customers. Maybe there's new regulations, there's things that have to be changed. So when the code has to change, that old code, stringly typed code and all the other code, has to be modified and refactored at times. So I'd say it's not a bug, but stringly typed code is something that's going to multiply your cost. It's a cost multiplier or a speed bump. It's a little bit hard to sail in your cool yacht when it's covered in barnacles on the bottom, and I describe stringly typed code as something that just really slows you down from refactoring, from producing new features, because you're always worried about what you're going to break and not know what it is. And I should also say you can write it's a major source of brittleness in code. So this is what I was just saying about worrying about, well, if I change something over here, I have no idea. Maybe all the front end is depending on this thing, but there's no actual warning. There's no build tool that I run and it tells me, hey, you broke page 3, 5, and 7. It's just, you just run it and you see. And the problem with that is that maybe you run it and you don't see a problem, but your end user runs it and then they run into some huge problem. You can write stringly typed code in any language. It is not just something about dynamic languages that we mentioned before. You can do it in static languages just as easily. So I mentioned also that it's a coding pattern involving trivial errors. Now, I just want to be clear that we're talking about trivial code changes that you might introduce when you have to do a new feature. I'm not saying the outcome's trivial, because otherwise the whole talk is trivial. The outcome could actually be really major. It could be bugs in production that cost money to rectify. But what we're talking about is bugs that you could introduce by just changing a couple of letters in your source code, and then having no warning until the thing slips all the way out into production. So yeah, stringly typed code can be a big deal. The other thing about these errors is that they are possible to detect without even running the code. You can look at the code, and if you look well enough, that's what code reviews are for, right? But also that's what static checkers are for, build tools, compilers, and so on. These are the kind of errors that can be checked statically. So in the talk later on, I'm going to go into detail into a whole bunch, and so I'm just going to really briefly outline a sort of a list of these sort of errors that we're going to come across. So the first one is kind of the bread and butter of type systems, and that's typos. So I've just got an example there where I'm referencing a property, and I've got two different spellings. One's right, one's wrong. Depending on your system, you may not find out about that until later on, and depending on when that piece of code actually runs. So another stringly typed error is when you've got implicit connections between different parts of your system, but there's no tool that can actually work out that these are the same concept. So here I've got an example where you've got some state in your code, and over somewhere else in HTML, you're using some sort of templating language to get that piece of state displayed on the screen. But you may have a system that either does or doesn't make a link between those two things. So if you go and refactor your state, do you find out that your front end is broken? Well, it depends. And we'll look at some techniques around that later. Another one is transposed values. So, here's an email function. We're sending an email. There's Alice, Bob, hi, and hello. Is it really obvious from looking at that who's the sender and who's the receiver and what's the subject and what's the message body? Well, you probably have to go and look at the implementation of the function. Some IDE tools will help you and they'll tell you which one's which, but even then, if your variables aren't named very well, the compiler's not going to tell you if you put them the wrong way around or change something, do it in the wrong order. So that's transposed values. This one I just call apples to oranges, because most programming languages, they have a type called a string and a very closely related one called a number. So stringly typed code is not always about strings. In this case, I've got an example that's about a number, but you can do this kind of thing with strings as well. So I've got a variable called m, and I'm calling feet to meters and passing in m and getting back something which I'm calling f. So you can kind of see the problem here is that we've mixed up feet with meters and we've called a function converting the wrong way, but the type system, it's going to allow it because they're both numbers. It doesn't know the difference between one and another. That's a units of measure problem. Another problem is conflicting definitions, and a classic example is systems that rely on feature flags or something, maybe picking up from environment variables, and you look around the code base and you see references to environment variables embedded in different files, and sometimes you'll see the same environment variable referenced in different places, but perhaps parsed in different ways or given different defaults. So I'd call that stringly typed code, because you've got different things that are supposed to be one thing, but they're actually possibly out of sync with each other. And if you change one, it doesn't necessarily tell you that you've got something else that's now inconsistent. And finally, we'll look at brittle control flow. So it's really easy to actually write control flow constructs using strings. Is an example there where we're checking if something is a heads, we do one thing. Otherwise, we do something else because it must be a tails. Well, unless someone actually sent something other than heads, and then you're going to get some wrong control flow. So going back to our definition, we said these are the sort of errors that pass static checks. Static checks is just when either humans or tools inspect the code, the source code. You don't even have to run it, you just look at it. So to pass these checks, it just means that your IDE is not telling you anything, or if you're using a text editor, it's just text, so you don't get any warnings there. If you've got a build step, that's saying, yep, it's all fine, no problems at all. You yourself don't spot any errors if you wrote this code, and a reviewer doesn't spot any errors. So that's what we mean. It gets all the way through the process. I should just briefly mention unit tests, because this is the classic thing. If you're in a dynamic language, you should rely quite heavily on unit tests. So on a technicality, they're not static checks because you have to run the code to actually run the unit test. But they run so close to your code that they're obviously really good and really valuable. There are a few drawbacks with them for our purposes today. First of all, you don't get any help in your IDE from unit tests generally. Also, they're human written, so they suffer from a lot of the same problems that the code itself. Basically, like if a human could write perfect unit tests, they probably don't need them. So tests tend to have flaws in them. They might have bugs in them themselves, and they usually miss coverage of your code. So they're definitely useful, but they're rarely as good as something that can be automated to cover 100% of what kind of errors it can detect. And finally, failing at runtime. The later you catch an error, it's often more costly to fix, as this bridge illustrates, which is a fake, by the way. There can be costs on your end users, and that may then, well, not costs, like hassles or inconvenience or reputational damage, whatever. These costs come back onto your own company, and yeah, the impact on your business, reputation, lost revenue, and then engineering costs to rectify these things. So those costs can really escalate. So stringly typed code, it's not trivial, really. It's something that really impacts businesses. Okay, moving on. I just want to come back to how I said in the room, we've probably got people coming from dynamic language backgrounds, static language backgrounds. I think that they often really shape how we think about solving problems with code. So I just want to focus on that for a little bit. So remember I showed this diagram before, we had some static and dynamic language people. There's something that Barney Strausstrup, who was the inventor of C++, once said. He said there's two types of programming languages. There's programming languages that everyone complains about, and there's programming languages that nobody uses. I think it sort of goes to show that there's a bunch of memes around languages, basically. There's things that people love to hate about all the different languages, maybe the ones you're using, maybe the ones that other people are using. So just for a moment, let's just take a look at some of these memes, not just the bad side, but also the good side. So let's start with dynamically typed languages, things like JavaScript and Python and things like that. Supporters might visualize it this way. Super fast, rapid development. You're really productive in these languages. Nothing slows you down. You just type it out and you run it. If it doesn't work, just tweak it, run it again until you get it right. You've got a prototype out the door in no time at all. They're flexible. They're really low friction. There's not a lot of ceremony. You just get stuff done. And you can usually, with these languages, you can really express a lot with a small amount of code. Okay, people who are detractors of dynamic languages, what sort of meme might they put on this? So the one I came up with was this guy. It's said that sometimes with dynamic languages, you just throw code at the wall and you see what sticks. They often don't catch basic errors, and that's a lot of the sort of things we're talking about here. Even typos can slip through and not be found until later on. And if these systems get large, they can really cause some refactoring nightmares. And I've had a few of those nightmares myself. So let's go across and give the treatment to the statically typed languages now. So starting with the good stuff, I just thought that was a nice visualization of really smoothly running orchestra of machinery. And that's statically typed languages like Java and C# running with all their factories and things. Everything is a symphony. Also, they catch your errors right away, so you're not likely to put buggy stuff out there because it catches a whole bunch of stuff straight away for you. So that's good, and there's lots of great tooling for these languages, and you can really scale up. They're designed for that. On the detractors side, I came up with this one. So there's a toilet there, and we're just trying to flush the toilet, but there's this whole massive machinery. And this is kind of the rigmarole of what you sometimes run into depending on the kind of project you're working on. But basically you've always got to appease the compiler. Your thing's not going to run until the compiler is satisfied that it can prove that there's no type errors in your code. So you've got to come up with types. You've even maybe need to change your API to match what the compiler is able to do. And often you end up with a lot of boilerplate code changing between the types that you came up with, or the classes and so on, to some sort of text representation that you can store in a database or send over HTTP request. And finally, abstract singleton proxy factory bean. So I thought that was a sort of a made up thing, but I Googled it and it took me straight to the documentation page for the actual thing. So it's a real thing. Complexity we're talking about here. Okay, they seem like they're really different ends of the spectrum, but what about common ground? I think we can all agree that errors are best caught as early as possible. This is from the NIST in the USA. They did a study and they basically neatly demonstrated that the earlier you catch a bug, I know that these labels are really small, but basically these are costs going up the later you find a bug. So that's production right over there on the right side. And here the second one is when you're actually writing the code. So the ideal time to catch a bug is back here, even before you write it preferably. But if you're the coder, you just get given, okay, do this. That's where you want to catch your bugs. You don't want them to slip out further than that. So this is a point in favor of languages with the static checking step, because they're going to catch a lot of these ones early. And it's also a point in favor of tools, good IDE tools, because they're going to just show you little red squiggles and so on. Another thing we can probably agree on is that all code and data does have types. Even if you're in a dynamic language, types are just the static facts about the data in our programs. So they might be explicitly written into your code, or they might be implicit, and you've got to basically like run the program in your head to work out what the type of things are. But either way, the types are there. They're definitely there. So another way of saying that, there's no such thing as typeless or schemaless. There's just type implicit or implicit schemas. So, you know, things like dynamic code, JavaScript, Python, things like that, schemaless databases, no SQL, things like that. On the other hand, types can be explicit. They can be part of the code or part of the system. So relational database schemas, they're explicit types. You can only do what the explicit type says. Things like classes in Java or C#, they're basically dictating what you can and can't do with a piece of code, and it will not allow anything that doesn't match the type. So they're explicit types. More common ground, code. It's for people and machines. It's not just for machines and it's not just for people. The machines have to be able to read it and process it and execute it, but people are usually the ones who write it, so far at least. So what does it mean? Well, types help document and communicate our intent. So that's on the human side. So if you've got no types that are explicit in your code, then you've got other issues with other people coming along later and maybe not understanding the nuance of what you were trying to achieve. And that's where if you've got stringly typed code in there, it can easily be changed by someone else who doesn't understand the very careful way that you were thinking of it running, and then they've violated your ideas, but none of it's explicit. So, even in a system like, say, Express in Node, it's a web server system. It's not written in TypeScript, it's written in JavaScript. There's no types in the system, but you go to the documentation and it's basically just showing you a whole bunch of types. It's showing you what all the properties are and what types of values they accept, what all the functions are. So the types are there. It's just, are they explicit in the code? Are they executable documentation, or are they kept in a separate place? Another point about this people and machines, programming languages and their type systems, they can be more or less expressive and they can be more or less obtrusive. And the point I want to make here is that if types and static types solved all of our problems, then why are dynamically typed languages and NoSQL systems thriving? It's because they're low friction and they're really great in their niches. So we haven't really nailed it with type systems. So I'm really aware that I'm not saying like, hey, do everything in types. I'm saying types solve some problems and introduce different problems. So there's trade-offs. Yeah, simplicity versus complexity. Okay, so the TypeScript way. I'd like to imagine an elevator pitch by Anders Heilsberg, who invented TypeScript and a few other languages, well-known ones before that, like Delphi and C#. Given all these trade-offs, how he might pitch the idea for TypeScript. And it'd be something like this. What if types were optional and they could actually describe our real-world coding patterns? So the idea would be, you smash out some code, you do it dynamic code style, right? You just get it working. Don't worry about appeasing the compiler. And then you have this type system that you can come along later and say, okay, now I want to lock this in and say, this is what's allowed, this is what's not allowed, and you can add this on later on. And in fact, that's how TypeScript largely started. Most projects weren't written in TypeScript at the time that it started, or very few, or none when it started. But what it could do was actually create type definition files for existing libraries, things like Express and all kinds of things that were really widely used out there. And it kind of bootstraps that way. So you could want to do something with strong types, and then you could just get the types from this definitely type repository and then use Express or use, I mean, even now you can do that. You can use React, you can use whatever you want. Whether or not those things are written doesn't matter because the types are bolted on. They actually describe what this API does. So you can design an API without worrying about, oh, will this work in a specific kind of type system? No, you just use the types to model what's actually going on. And what you get in the end is something that looks really different from some of our better known static type systems. Do you know the book Design Patterns, Gang of Four? It's pretty well known. I really liked reading it at the time, but years and years later, I've come to realize with other systems that a lot of those patterns actually start to look like workarounds for things that the language or the type system can't easily express. So for example, decorator pattern, that's one of these design patterns from this Gang of Four book. I just wanted to illustrate a diagram of, it's a class diagram with decorators, there's some interfaces, there's some concrete implementations. I won't go into all the details of that, but if you have to actually do a general purpose decorator in a typical object-oriented statically typed language, it can be really difficult. And I remember trying to do some of these, trying to solve the general problem, not just for this one specific case, and you end up with reflection code where you go through and try and work out what the type actually is at runtime, write some code to do the thing that you're trying to do with it to decorate it in some way, and then you use this emit code to, at runtime, generate new DLLs and things that you can then inject into your running code. And in the end, it's really, really complicated. In JavaScript, here's a spy function. I want to just wrap any function you give me so that when I call it, something gets logged out, and it logs what the arguments it was called with and what the return value was. And that's the whole thing there. So here's my spy function. I just pass it a function, and it's going to return another function that has got this spy built in. So there's the function it returns. Here's it calling your function. Here's its logging, and here's it's returning the return value. So you've just wrapped a function. You've just decorated it in a couple of lines of code. And here's the TypeScript definition for that. It's just basically saying, well, the type of this thing, spy, it takes a function of a specific shape f, which we've made generic. So whatever shape of function you put in, we'll call that f, and it returns one of the same shape. We've just modeled what you've done. So the actual implementation was super easy in a dynamic language. And then the type description is 100% accurate and also extremely easy to express. So we're talking best of both worlds, ideally. Rapid prototyping, short succinct code, accurate type checking, and it's type safe and it's scalable. So that would be the elevator pitch. Do both. But how would you actually achieve that? So that's where it comes down to the actual type system. Starting with types that model what we actually do. So for example, in TypeScript, you can have single values that are actually types. So we've got an apple type and an orange type, and you can only put the string apple, that lowercase set of characters there. That's the only thing you'll accept. If you try and assign a value pair to a variable that can only accept this apple string, you just can't do that. So they're all strings. But the compiler has now got visibility into what is allowed in those strings. So it's not just one big bag of any possible sequence of characters all being the same type. So these are called unit types or literal types. From there, it's sort of obvious that you want unions of types. And this is another thing that a lot of languages find it very hard to express. So a coin toss is just, we want to express that in our program as the string heads or the string tails, and we don't want to accept anything else because we don't want to have like typos and things going on. So we can have a type coin toss, and we can write a function that accepts a coin toss, and they're the only two values it's going to accept, and the compiler will check that and it won't allow anything else. Intersections of type. These are one where it's a little bit harder to explain, but the example I came out with here is that, imagining we've got a couple of objects which are just full of properties. They're just sort of record types. So we've got one with a foo numeric and a bar string property, and we can merge those two types together. What would be the type of the resulting type of merging these two things together so that they had both properties? Well, it'd be the intersection. A and B, it's the intersection of those two. So you can just express that in the type system. You can write this code that merges things, and then you've got a type that describes what the result would look like in a static way that the compiler can actually check. Another really interesting development with TypeScript is narrowing. So here it's really common to have things like nullable types. So here's an example where we've got a date, but we're not sure. It might actually be undefined. Maybe it was an optional property from somewhere. If we try to call a property on that with TypeScript, it's going to tell us that we can't because it might be undefined, and you can't do that with undefined. So statically it's saying, that's not right. There's a red squiggle there in your IDE. Here we've got a type guard. So we're actually going, well, if date's not undefined, now I'm doing exactly the same thing. Syntactically, it's exactly the same thing, but now it's okay because it's narrowed the type. So that inside that block, it recognizes, well, the type's not date or undefined anymore, it's just date. So it allows this thing. And this can get really sophisticated, and it just models what you actually do in your real code. Finally, structural typing. So what this means is that most type systems are nominal. So, you know, if you need to pass an instance of a certain class to a function, you've got to get an instance of that specific class. You can't just pass in something that's got similar properties or whatever. The opposite of that is a structural type system. Basically, it's duck type. If it looks like a duck, quacks like a duck, it's a duck. So our options object here takes a name and account, and here I can just simply make up my own object that's got a name and account and pass it in there. I don't need a constructor. I don't need to find out where your options object constructor is or a factory or anything like that. I just make up an object that's got a name and account. That's fine. It's as good as anything else. I couldn't resist just putting this quick slide in here because the types can get really, really sophisticated. Someone pointed out a while ago that the type system is now Turing complete in TypeScript. I've got a little demo here of what someone did with that. So I'm not suggesting you do this at home, but what's happening here is, it's not running it. Yeah, it is. This is basically some database records, but here we're getting the type of these records, and TypeScript is able to infer all the specific strings and numbers and things in there. And then these are some queries actually run at the type level. And okay, it doesn't actually seem to be running. Okay, technical problem there. But what goes on is that these strings are actually these literal string types. And if you hover over the types here, it actually shows you the result like as if you just executed this query and it'll list Bart and Lisa and things like that. And you can go and change that, but none of this is running. There's no program running here. If you run this, nothing happens because the types don't exist at runtime anymore. So these are just running in the compiler. As you compile the code, you modify the code, it's basically able to do arbitrary computations. Maybe not so useful thing to do in most of our code, but it is very useful for other things like accurately typing REST APIs, GraphQL APIs, things like that. Okay, finally, let's go into some more specific ones and see if we can just type some code the way these StringlyTyped examples that we had in the beginning in a safer way. What we're going to try and do is aim for 100% accuracy with our types, but also trying to be really unobtrusive, because I think that's what TypeScript really brings to the table. So that first one, I'm not going to spend really much time on this. This is the bread and butter of type systems, right? So here, you know, we've got some things that are right, some things that are wrong. Maybe the APIs aren't even consistent, so everyone's going to make mistakes like this. You can't really get around it. And that's generally not a problem if you're already using static languages. They're all over that. The thing to remember is that properties in dynamic languages are effectively strings. They're looked up as strings. So it doesn't know, a dynamic language doesn't know if that's correct or not, because it's basically looking up a property bag and just seeing at runtime if it's there or not. So with TypeScript, you can say, no, it's not just a property bag, it's got these specific things on it. So the solution here really is just to use TypeScript or some other statically typed language. You won't have typo problems anymore, so let's move on from that one. The second problem, we mentioned implicit connections between things. So there's a little bit more of a fuller example here now, but still very simple. So this is a single file component in Vue. I've got a template up here. What I want to note is that effectively this whole template is a string. It's opaque. The compiler can't work out what that means or what it is. So down here, this is already in an error state, because up here we're trying to inject something called name, but we don't have name down here. We've got first name and last name, but there's no build error. There's no warning there. So how can we improve on that? Well, in this specific case, I really think this is a strong case for using things like JSX or TSX, where you actually do your HTML templating or your HTML view. You do it in the code. The reason for that is that the type system now in TypeScript is able to work out that there is a single definition of this name and that this refers to the same one. If you refactor name, it will automatically change this. If you just type something different there, you're going to get a red squiggle here because there's going to be nothing called name. So you can get rid of your problems in this case pretty easily like that. There's other examples we could do, but I'm just going to move on to others now. We talked about these transposed values. I had that sending email and you couldn't really work out which way around it went. This is the classic Mr. Bean problem when he's trying to do his own filling and he realizes at some point that the dentist thing can go all kinds of ways. So how does the type system help here? Well, it really can't because they're all strings. It doesn't know what the correct order is. It's up to you to figure out that you pass the correct things in the correct positions because these are positional parameters. So this is StringlyTyped code. If you look up blogs on what is StringlyTyped code, you get examples like that. But I would say the solution is not really about the strings themselves. It's just about the positional ordering of the parameters. My preferred solution for this is just pass by name. And some languages have direct support for pass by name, but a lot don't. And in JavaScript, you can just basically say, well, instead of accepting 3 parameters, I'm going to accept a single parameter. And I've just called this one options. And it's an object. And it's got properties. And the properties are the things I want to get. And I'm just going to have this one parameter. Now, when you call it, here's the call down here. I've just basically fetched these host, user, and password from somewhere. And the only difference here is the extra curlies here because we're constructing a shorthand object with those properties in it and just passing that one thing to the function. So it's still stringy, right? Like there's still strings in there, but now everything has to effectively be named. The names are checked, they have to match, you can't have the wrong things in there, you can't have anything missing, you can't have anything additional that doesn't belong. And that just basically feeds off structural typing. Structural typing makes that possible. It's way harder to get this accidentally wrong. As a bonus, the order doesn't matter anymore. You can put these things in any order you want. Also, remember we were talking before about code tends to change, and one of the classic things that happens is that functions take on new options or new parameters. When you list them all out there, you might end up with, say, an optional one, and then someone comes up with the next API, you need another required one. Well, now you've got to have sort of weird overloads and do a lot of stuff. Here, you can make any of these optional, you can add new things all the time, and you're not going to break the API. You've just got additional things that weren't supported before. Okay, now this fourth problem, we were talking about apples to oranges, and the example I had before was feet and meters, so we had units of measure. And now I've got one that's actually string related. So I've got a function that sort of, by looking at it, it looks like what it wants is an absolute path, and I've called it with a relative path. So semantically, there's an error here, but the type system is not helping me because, in fact, an absolute path is just going to be a string, and this relative path is just a string. A string's a string, so I can pass that. The compiler says, yeah, it looks fine to me, and then you maybe do the wrong thing at runtime, delete the wrong file, send the wrong person the wrong information, whatever. I mean, how could we work around that? How is the type system going to be able to tell a relative path from an absolute path? That's one where TypeScript has got some tricks up its sleeve. The first one I'll look at is wrapper types, and this is more of a classic approach in a lot of sort of object-oriented type systems where you'd create a class and you'd wrap that, and so basically now your API is going to revolve around instances of this absolute path class. So you can't just pass in a string, you've got to instantiate this absolute path or get one from somewhere, maybe from some other API, and now you can process a file because that's the only thing it's going to accept. It works, it's good, we got rid of the strings, but it's actually not my preference because it introduces marshalling and conversion boilerplate. You've got a type now that you've got to worry about, and if these things were going to and from a database, whatever, you probably just want to store the path as a string, right? You can't store the actual class. So you've got to have conversion codes, serialization, deserialization. It doesn't quite look like the simple version we started with. We've added complexity. And it doesn't interoperate as easily because now you've got your own custom way of handling this specific data type, but absolute paths work in lots of places, right? But yours don't now. Also, it's still easy to construct a invalid path, but with no early warning. So here's one where I've just passed the relative path to the constructor. It'll fail at runtime, but the whole point here that we're talking about is trying to catch errors early, right? So could we do better? Could we make it fail even earlier than that? So my preferred solution here is what's called branded types. This is still a stringy solution. It's got a weird thing here where we're just saying the absolute path, yeah, it's just a string, but we're using this intersection type and we're saying it's a string, but it also has this weird extra property with this brand in it, absolute path brand. Just to summarize, a branded type is thing that only exists in the compiler. This all goes away at runtime, and in fact, the only reference to this property is here in this type. We never at runtime, when we're checking if something's an absolute path, we never actually give it this property, or we don't actually check for the property. So what is going on here? Well, we've got a couple of advanced types in here. I won't go through it all, but let's just go through what's happening down here. So it looks a bit like the last one, where now we need an absolute path, but it's actually just a string. So we can just we can have a string here. So this is an absolute path, and we're calling process file, but it's not satisfied because it doesn't know that this is an absolute path. It's just a string. So it's going to say, no, you can't do that because this thing requires an absolute path, which has this extra brand thing on it. And this one doesn't have a brand, it's just a string. So no, you're not allowed to do that. Well, that's good. We didn't want that to work, but I mean, you can't pass any string to this now. So how do you satisfy it? Well, this is the magical part. So we've got what's called a type guard here. So we're saying, is this P an absolute path? And this is just a Boolean returning function, just returns true or false. But actually the return type annotation is basically saying, if this returns true, you have established that P is an absolute path. So the compiler works backwards. It also has special handling for assertion function. So it says, when we get to this last line, which is now okay, by the way. So here, this one didn't build, but this one, exactly the same with exactly the same string, this one passes. So something special happened here. The compiler reasoned that the only way we could get to this line 19 is if the assertion succeeded. Otherwise, it would have thrown. We never would have gotten there. Oh, computer's going to sleep. So the only way the assertion could have passed is that this function returned true. So basically our type guard failed. The type system knows statically without running your code, the only way you can get here is that this returned true. And if this returned true, you've told the type system that that must be an absolute path. So you check it at runtime, but the type system knows, well, when you're calling it here, it must be an absolute path. So we've effectively taken a general type like string and we've branded it with additional knowledge that can now be used in APIs, passed around the system, and the type system can reason about that. And the cool thing is that you end up with simple strings in the code. You don't actually see the types down here. You basically just write your code as you did, and it'll warn you when you haven't checked something, and you put in some runtime checks, which is really what you want because they're going to catch those. But your errors are going to happen statically. You're going to be told straight away. So another one of the problems we looked at was conflicting definitions. So we've got environment variables. Process.env in Node is where you access your property bag, which is full of the environment variables. You can't avoid these being strings. The property names of the environment variables are strings, and the values all come through as strings. And these are from outside the system boundary. So you can't type that. You can't tell it, well, this is what's going to be in the environment. Well, you don't know. You run the program. It could be anything in there. So this is kind of like a standard approach, right? Because you're just you would do this in a statically typed language as well. You'd have a kind of property bag. You don't know what's in there. You reach and you look for a stringly named property, and you've got a string value, and then you might do some things to it, convert it, apply some defaults. But we've got several problems in here. These aren't actually consistently doing the same thing. So this one treats foo level as a number. No, well, that's fine. Let's look at this one. So the foo enabled, it comes in as a string, but if it's not present, then it gives it a value of 1 as a string, and then it parses that. So this is actually kind of clever, right? So it's like in your environment, you could pass a 1 or a 0 or the word true or the word false, and when you parse that, you're going to get a truthy or a falsy value, and then you do your stuff. But down here, here we go. So we're using foo enabled, but we're just checking the raw value. So basically, if it's not present, then it's not enabled. But if anything is present there, the string true, the string false, this is all truthy to JavaScript. So if you put in the string false, that check is going to go, oh, it's actually enabled, and it's going to run the wrong piece of code. And there's no early warning for that. And we've got one down here, and this is particularly insidious for brittleizing systems, making systems brittle, is that we're not actually literally referring. So even if you did a search looking for all the instances where a particular environment variable was referenced, you wouldn't find them here because we're actually dynamically coming up with the names, mapping, and then checking them that way. So there's a few problems in there. The main solution I would come up with here is just still a stringy solution, because like I said, you can't get rid of those strings out of the environment variables. But what we can do is we can put them all in one place, single source of truth, have a single config file. That's the only place that's allowed to read from process.env. What you do in there is you do all your validation, all your conversions, and all your defaults. They all live there. The rest of your system, this is what we had before, but now it's referring to those. So you take in all of that loose, messy, outside world stuff, but you expose inside your system something neat, typed, single source of truth, completely consistent. So we're still dealing with strings, but we've just changed the way we've written that. We're going to we won't have all these problems with inconsistent definitions or refactorings anymore. Final one, brittle control flow. So I've got a slightly different example here, which we're calculating the area of a square or a circle. It's important to read this comment, right? Because what it's doing is it's saying, well, if it's a square, then we square the length. If it's a circle, we do this. But the default case, well, we never reach here, lol, so let's just return 42 because it's the same type and we're not going to reach there anyway because we've told them right at the start that it's only for squares and circles, right? So they shouldn't pass in anything else. But of course, you know, someone has actually passed in a rectangle, and instead of getting an error or something like that, they're actually getting the number 42. Also, the person who actually put in the legitimate square also got 42 because there's a spelling mistake in here because it's just a string and it doesn't know what these strings are. And the person who passed in a circle got not a number because there's a typo in the radius up there. So that's why I call this brittle control flow. There's so many things that can go wrong and you don't find out about any of these things until runtime. So the classic solution in OO would be to actually create a hierarchy of types, have an abstract base class for a shape, create a square class, create a circle class, do things like that. And then the area function would actually be a method in there. And so each of these would implement its own. It solves a problem. There's no more strings. It's not my preferred approach though, because again, you end up with this kind of conversion boilerplate. So now if shapes were things you were storing in the database or receiving over the wire, you've now got to marshal them to and from your representation of shapes. So you've got this additional complexity in your code. Also, that's for another talk, but there's taxonomy problems with these classic, you know, single hierarchy taxonomies. It's not really easy to model everything in that constrained way. There are solutions for that, but we won't go into that. But it can get hard, it can get boilerplatey, and also you still don't have a lot of control over subclassing and things like that. So it's not my preferred. I think we could do better. Another classic is using an enumeration. So now it's like, well, we can only have shapes and squares and circles now because we're going to create an enumerated kind and our shape is going to have only one of those kinds. So the compiler can check, it can only be this or that. But there is this extra information we've got to drag around and not everything has everything. So we've got like optional length and optional radius because some things might have a length, some things might have a radius. So now it looks a bit like our original code, but instead of strings, we've got enumerated types. So it's cool. We can check those, and if you put in the wrong thing, it won't build. The issue is that you don't get strong checking over here because they're all optional properties and anything could use anything else, and you're not really sure which one's which. So I think we can do better than that again. So my preferred approach is actually what we'd call a discriminated union. So now the actual function itself looks pretty much identical to the original. What we've done is we've introduced a square type that just has a kind square and a length, and a circle type that has a kind circle and a radius. So that's the only thing that a circle can be. It's the only thing that a square can be. And our shape is now just the union of the two. A shape is a circle or a square. It can't be anything else. Now we can actually pass in, using structural typing, just instances of squares and circles. We get the right things. All of this stuff has to be correct. It won't build otherwise. You can't have typos here because it's like, well, that is not a valid circle or that's not a valid square. You can't refer to the length on a circle or the radius of a square because it works out when you're in here, it narrows the type down and it knows it can only be that thing. And the other thing is, often in systems when they expand, you get new cases, right? So if there were new cases, how would we know about it here? Well, the type system can also work out the exhaustiveness of your casing. Or if you've deprecated and removed one, it'll tell you, well, that's no longer a valid shape. So as you maintain and change your system, you get all these early warnings, which is really great. Okay, so in conclusion, good strings are good. Don't believe what you've been told, never use strings. Strings are bad. It really depends on the tools that you've got. So I'd say the key takeaways are explicit types, first of all, is what we covered earlier on. They really help humans and tools. And in TypeScript, I would say when it comes to stringly typed code, feel free to keep using strings. Just make sure that they're part of the type system, that there's visibility on them. So they're often natural, they often keep the code simple, and they make it look like what you'd write if you were writing dynamically, but you can make them really strongly checked, and they help you avoid a lot of conversion boilerplate. Make sure you've got a single source of truth, because that's another thing that bites you in a lot of these cases. Aim for 100% accuracy. Why not? You know, if you can model just about anything with a type system, then don't leave gaps. Make it really accurate, and then you'll catch all of these things before you go to production. And finally, this is a preference for me. Make your types as unobtrusive as you can. So you want to model the natural solution, the thing you'd write if you weren't worrying about the types. And you know, TypeScript's really good for letting you be able to do that. Ideally, an API should look like the untyped code, and it won't even be full of type annotations. They'll all be inferred, and it just helps you avoid boilerplate. So that's it. Thanks for listening. Any questions?